Welcome to today's session. In this tutorial, we're going to explore how applications can be executed from different memory regions on the PolarFire SoC using SoftConsole. We'll start with loosely integrated memory, also known as LIM, where full debugging support is available. After that, we'll move on to running applications from eNVM and DDR using production-ready release builds. All demonstrations in this session will be performed on the PolarFire SoC Discovery Kit. Let's get started. Before we begin the demonstration, let's quickly review the setup requirements. For this session, we'll be using the PolarFire SoC Discovery Kit as our target hardware platform. SoftConsole will serve as our IDE for building and debugging the applications. And finally, we'll use a serial emulator, such as MobaXterm, to monitor the UART console output. On the screen, you can see the PolarFire SoC Discovery Kit, which will be our primary hardware platform for this session. Start by powering the board through the USB Type-C connector. This will supply both power and the debug interface used by SoftConsole. You'll also notice the microSD card shown here. While we won't use it immediately, it will become essential later in the demonstration when we run the application from DDR. The DDR execution flow uses the SD card to load the program image, so make sure the microSD card is available and ready to insert when we reach that section. With the board connected and all required components prepared, the hardware setup is complete. Before we begin running any bare metal applications, the Discovery Kit needs to be programmed with the latest reference design. This slide shows the full flow we'll follow: downloading the design from GitHub, opening FlashPro Express, and programming the board. Let's walk through the steps. First, we'll open the PolarFire SoC Discovery Kit reference design page on GitHub. From the Releases section, we'll download the pre-built programming file for the kit. This package includes the FPGA design along with the Hart software services, or HSS. If you'd like to learn more about HSS, we've added a YouTube link in the description below. Before we move on to running the application, we need to connect the Discovery Kit to the PC. We'll use the USB Type-C connector for both power and the JTAG to UART interface. Now that we have downloaded the reference design from GitHub, let's go ahead and program the PolarFire SoC Discovery Kit. We'll begin by opening FlashPro Express. Here, we'll import the FlashPro programming job from the zip file we just downloaded. Once the job is loaded, we'll connect the Discovery Kit using the USB Type-C interface. With the board connected and the job ready, we'll click OK to confirm the programming settings, and then click Run to start programming. FlashPro Express will now configure the FPGA fabric and update the HSS firmware. After the process completes, we should see a Run Past status, confirming that the Discovery Kit has been successfully programmed and is ready for the upcoming LIM, eNVM, and DDR demonstrations. Let's open a serial emulator such as MobaXterm and connect to the COM port assigned to the Discovery Kit. We'll configure the connection with a baud rate of 115,200. As soon as the terminal connects, we'll see the HSS boot messages appear. We'll keep this terminal open for the rest of the demo so that all the outputs from LIM, eNVM, and DDR execution will be captured in the same window. Before we begin executing applications, let's take a quick look at the key memory components available. The first is the on-chip L2 cache. This 2 MB block can be reconfigured as 1.875 megabytes of loosely integrated memory, or LIM, with full ECC support. LIM provides fast, low-latency execution and is ideal for debugging applications within SoftConsole. Next, we have 128 kilobytes of embedded non-volatile memory, or eNVM. This memory is typically used for storing small bootloaders or compact production images that need to persist across power cycles. And finally, the Discovery Kit includes a 1 GB DDR4 memory device connected over a 16-bit interface. This external DDR offers the largest memory footprint for running high-capacity applications or workloads that require significantly more space than on-chip memory can provide. Together, these three memories, LIM, eNVM, and DDR4, give developers a flexible set of execution options depending on the stage of development and the size of the application. We'll begin by running the application from LIM. To get started, head over to the PolarFire SoC bare metal examples repository on GitHub and download the complete package. Inside the driver's example folder, navigate to the MSS section. Here, you'll find a project named MPFS UART interrupt. This will be the application we use throughout the demo, and will run the same code from all three memory regions, LIM, eNVM, and DDR. Next, open SoftConsole and create a new workspace. In the Project Explorer, click on Import and bring in the UART bare metal example. Once the UART bare metal example is imported, you can explore the complete application structure inside the source folder. Each Hart, from Hart 0 to Hart 4, represents one of the RISC-V cores inside the PolarFire SoC. Hart 0, also known as the E51 monitor core, is responsible for system initialization and for bringing up all the U54 Harts. In this example, Hart 0 configures its UART, prints an initial message, and then raises software interrupts to wake Hart 1 and the other to U54 cores. Once that setup is complete, Hart 0 simply remains in an infinite loop while the rest of the application logic executes on the U54 Harts. Now let's look at Hart 1, also known as U54_1. This is where the main UART application runs. In this file, the Hart begins by configuring the UART, setting the baud rate, and bringing the UART out of reset. It then sets up both polled and interrupt-based transmit methods and registers an interrupt handler to process incoming UART data. When the application starts, Hart 1 sends a welcome banner, followed by a simple menu over UART. From here, any key you type in the terminal triggers different actions. For example, displaying debug information, showing the menu again, or sending messages using either the polled or interrupt method. The UART receive interrupt handler also keeps track of how many times an interrupt has occurred and prints out the count whenever data is received. In short, Hart 1 is responsible for running the interactive UART example, handling user input, and demonstrating both polled and interrupt-driven UART communication. Now that we've explored the application structure and the role of each Hart, let's move on to building and debugging the project. To begin, right-click on the project and select Build Configurations. Choose the LIM Debug Discovery Kit configuration. This ensures that the application will be built to execute entirely from the loosely integrated memory. Next, click on Build Project. SoftConsole will compile the code, link the application, and generate the ELF file for debugging. Once the build completes without errors, we're ready to load and run it on the hardware. Go to the Run menu and open Debug Configurations. Under the GDB Open OCD Debugging, select All Hart Debug. This allows the debugger to control all 5 Harts simultaneously. Keep the default settings as they are and click Debug. SoftConsole will now connect to the Discovery Kit and launch the debugging session. Once the debugger is launched, the next step is to open the UART terminal to view the application output. Click Resume or Run from SoftConsole window. This starts the execution of the bare metal UART example. You will then see the UART output appear in the terminal window, including the welcome banner and the interactive menu from Hart 1. At this point, you can type commands directly into the terminal to interact with the application and observe the RISC-V cores responding in real time. Now that we've completed the LIM execution demo, let's move on to running the same application from eNVM. First, we'll terminate and remove the LIM debug session, as we no longer need the LIM configuration. To run the application from eNVM, we'll switch the build configuration in SoftConsole to the eNVM release Discovery Kit option. This configuration generates a production-style image that is linked to execute directly from the on-chip embedded non-volatile memory. Once this configuration is selected, we'll go ahead and build the project. Now that the eNVM release build is ready, let's program the application into the device's embedded non-volatile memory. To do this, we'll use the built-in external tool provided in SoftConsole. We'll start by clicking on External Tools in the toolbar and then selecting External Tools Configurations. In the configuration window, we'll choose the option titled PolarFire SoC Program Non-Secure Boot Mode 1. This utility programs the compiled application into the eNVM and prepares it for execution at boot. Under the Arguments section, we'll enter the die and package details for the PolarFire SoC Discovery Kit. Once the parameters are set, we'll click Apply and then Run. SoftConsole will now erase the eNVM, program the new application image, and verify the contents. Once the eNVM programming is complete, the application is now stored inside the device's on-chip non-volatile memory. To run it, we'll simply power cycle the Discovery Kit. Unlike the LIM build, which disappears after a reset, the eNVM build automatically starts running as soon as the board powers up. So after the restart, we'll look at the UART terminal, and here we can see the application output appearing immediately. This confirms that the code is now executing directly from eNVM, without requiring the debugger or SoftConsole. Let us now move to running our application from DDR. Since in the previous step, we programmed eNVM with our bare metal application, we first need to reprogram the Discovery Kit with the reference design job file, again, using FlashPro Express. If you need a refresher, you can go back to the earlier section where we demonstrated this process. This step restores HSS in eNVM and ensures that HSS functions as the bootloader for loading our DDR payload. Next, let's open SoftConsole to prepare the application for the DDR release build. Before we compile, we need to make a few configuration changes so the application runs correctly when loaded by HSS. First, we'll limit the application to run only on Hart 1 and Hart 2. To do this, we'll go to the source folder, then open Platform, followed by Platform Config Reference, and finally the MPFS HAL config directory. Inside this folder, we'll open the file msssoftwareconfig.h. In this file, we'll set macros, MPFS HAL first Hart to 1 and MPFS HAL last Hart to the value 2. This ensures that our application is running on U54_1 and U54_2, also a bootloader running on E51 loads application to the target memory and kicks off both Harts to run it. Next, we'll modify the macro image loaded by bootloader and change its value from 0 to 1. This tells the application that it will be loaded by HSS instead of running directly from memory. After making these updates, we'll save the file. Now that our configuration changes are complete, we're ready to build the application for DDR execution. To do this, we'll switch the project to the DDR release. Discovery Kit Build Configuration. We'll right-click on the project, go to Build Configurations, and select Set Active. From the list of available configurations, we'll choose DDR Release, MPFS Discovery Kit. This configuration links the application to run from the DDR memory space and uses the appropriate linker script provided for the Discovery Kit. With the DDR release configuration selected, we can now build the project. This will generate the ELF file that we will later package into a payload for HSS to load into external DDR. With the DDR release configuration selected, we can now build the project. We'll simply click on Build Project, and SoftConsole will begin compiling the source files and linking the application using the DDR linker script. Once the build completes successfully, an ELF file will be generated in the build output directory. This ELF is what we'll use to create the DDR payload that HSS will load into external DDR during boot. Before we create the DDR payload, we first need to build the HSS payload generator executable. To do this, we'll start by downloading the Hart Software Services source code. We'll go to the Hart Software Services GitHub page, open the Releases section, and download the source code zip file. Once downloaded, we'll extract the archive and move into the HSS payload generator directory. Here we're using WSL to build the tool, so we'll open a terminal and navigate to the folder. The payload generator has a few dependencies that we need to install before building it. These include YAML support, ELF parsing libraries, and OpenSSL components. With the dependencies installed, we can now build the tool by simply running the make command. This will compile all the source files and produce the HSS payload generator executable. Once the build finishes, we can list the directory to confirm the executable has been generated. You should now see the HSS payload generator binary in this folder. This is the tool we will use to convert our DDR ELF file into a payload file, which HSS will load into external DDR during boot. Now that the HSS payload generator tool is built, the next step is to prepare our DDR application for packaging. We'll take the ELF file generated by the DDR release build in SoftConsole and place it into the test directory used by the payload generator. This is the same folder that contains the sample configuration file, config.yaml, which we will edit shortly. Placing the ELF here keeps everything in one location, making it easy to reference the file directly from the configuration. The next step is to edit the config.yaml file used by the HSS payload generator. This configuration file tells HSS where to load the application in DDR, which Hart should execute it, and how the payload should be packaged. Let's open the config.yaml file. At the top, we can optionally set a name for our image. This is mainly for identification and logging, so we can leave it as is or set any name we prefer. Next, we'll move to the Hart entry point section of the configuration file. This section defines the DDR start address for each Hart at boot. Since we configured the application to run on U54_1 and U54_2, we'll keep only these two entries and remove the rest. Here we'll set both Harts to start at 0x8 million, which is the base DDR address defined in our linker script, and we'll delete the remaining Hart entries because the application will no longer run on those Harts. Now we'll update the payload section. By default, the sample configuration points to a placeholder file. We'll replace that with the actual ELF generated by SoftConsole in the DDR release build. We'll also update the execution address to match the DDR load address and we'll add U54_2 as a secondary Hart so that both Harts participate in running the application. Finally, we'll comment out any unused example payload entries that come with the default configuration file to keep the configuration clean and focused on our single DDR application. Now that we've updated the configuration file, we're ready to generate the DDR payload. we'll use the HSS payload generator tool that we built earlier to convert our ELF file into a payload image that HSS can load into DDR at boot. From the HSS payload generator directory, we'll run the following command, pointing it to our updated configuration file and specifying the output location for the payload. The tool will read the configuration, process the ELF file, and create a payload.bin file inside the test directory. This file contains the complete DDR boot image packaged in a format that HSS can understand and load during system startup. Once the command completes, we can verify that the output file was generated successfully by listing the directory. We should now see payload.bin in the folder. This is the file that HSS will use to boot our bare metal application from DDR. We need to flash the payload.bin file onto the microSD card. For this, we'll use a tool such as Balena Etcher, Win32 Disk Imager, or the DD command on Linux. We'll select payload.bin as the image file, choose the microSD card as the target device, and begin the flashing process. This writes the payload as a raw image in the exact format required by HSS. When the flashing is complete, we'll safely eject the microSD card and insert it into the Discovery Kit. With the SD card prepared and inserted, the system is now ready to boot the application from DDR on the next power cycle. Now that the microSD card has been flashed and inserted into the Discovery Kit, we're ready to boot the application from DDR. We'll simply power cycle the board or press the reset button. During startup, the HSS running from eNVM will automatically detect the payload.bin file on the microSD card, load it into DDR at the configured address, and then hand over execution to Hart 1 and Hart 2. On the UART terminal, we should now see the same UART welcome banner and menu, this time coming from the application running entirely from external DDR. This confirms that our payload was successfully loaded by HSS and executed from DDR memory. With this final step, we've now completed our demonstration of running a bare metal application from all three memory regions on the PolarFire SoC Discovery Kit. We began by executing the application from LIM using SoftConsole for full debug visibility. Then we moved to eNVM, programming the application into on-chip non-volatile memory for persistent execution after reset. And finally, we ran the application from external DDR using HSS to load our payload from the microSD card at boot. Through these steps, we explored the complete execution flow supported by the PolarFire SoC, from tightly coupled on-chip memory to production-grade non-volatile storage and high-capacity external DDR. We hope this walkthrough helps you better understand how applications are built, packaged, and deployed across different memory regions. Thank you for watching, and feel free to explore additional examples and capabilities using SoftConsole, HSS, and the Discovery Kit.